We'll now go ahead and sketch the Bode diagram of another example. And so in this case we have a second order system, but it's overdamped. Because zeta is greater than 1. And overdamped means that the poles of the transfer function are real. So we can take this quadratic denominator and we can factor it into a term s plus 1 and a term s plus 200. Okay. And so if we wanted to sketch the Bode diagram for this transfer function, the very first step is to put the system into Bode form. And from inspection, we can see that it's So in order to sketch the Bode diagram of this example, the very first thing we need to do is to put the system into Bode form. And by inspection we can see that it currently is not in Bode form. And it's not in Bode form because of this term. We're looking for something that has the form ts plus 1, where here we don't have plus 1, we have plus 200. Therefore, in order to put it into Bode form, we need to factor 200 out. This term is okay because it's in the form ts plus 1, where t is equal to 1. So that first term is okay. We factor out a 200 out of the second term. Now the transfer function is in Bode form. The second step is you want to sketch the Bode diagrams of the components. Where in this case we have a simple gain, which is 1 over 200 if we factor it out front, and then we have two simple poles. One pole at -1 and a pole at -200. We then go ahead and sketch each of those components, where we have a simple gain and two simple poles, and we've memorized the shapes of those Bode diagrams. So here again is the components of our larger transfer function put into Bode form. We'll sketch the Bode diagrams of each component separately, and then we'll add the components together. And we'll start with the magnitude plot. So thinking back to what the magnitude plot of a simple gain is, it's simply a straight line at the point 20 log k, where in this case k is 1 over 200. So 20 log 1 over 200 is approximately -46 dBs. So that's the magnitude plot of component A. We then have a simple pole, where the magnitude plot of a simple pole starts out at 0 dBs at low frequencies, and then it has a break at 1 over t, where in this case our t is equal to 1. So then 1 over t is also 1. And at that point the slope breaks downward at -20 dBs per decade. And while we don't need to exactly identify where the two components cross one another, it's still helpful to get a rough idea. So looking at this, we're going down to -46 dBs. If we go over 2 decades, 1 decade will take us down -20, and a second decade will take us down to -40. So at -40 we're not quite to -46. So 1 decade over, 1 factor of 10 brings us to -20, another decade brings us to -40. Looking at the third component, we have another simple pole. In this case, t equals 1 divided by 200. And so 1 divided by t is 200. That'll be the location of the break for that simple pole. So we start off at 0 dBs, and then at 200 we break down at minus 20 dBs per decade. That's component C. The third step in this procedure, once we've drawn the magnitude plots of the three individual components, is to sum the Bode diagrams. And so looking at this, at low frequencies, we have two components that are flat at 0 dBs and a third component that's flat at minus 46 dBs. So the slope at low frequencies is going to be flat, and the magnitude is going to equal 0 plus 0 plus minus 46. And it stays that way until we reach 1 radian per second. That's where one of our components has a break frequency. So everything is flat. Once we reach 1 radian per second, then one of the components starts to go down at minus 20 dBs per decade. So we have a component with a slope of 0, slope of minus 20, and a slope of 0, where 0 plus minus 20 plus 0 is minus 20. Therefore, the total slope is minus 20 dBs per decade. And that continues that way. So we're flat, and then at 1 radian per second we start to go down at 20, and it stays that way until we have another break at 200. And so at 200 radians per second, when we're above that frequency, component A is still flat, but now we have two components that are going down at minus 20 dBs per decade. So minus 20 plus 0 plus minus 20 is minus 40. And so then we'll go down even steeper. So we have something that looks like that. And if we recall the things that we need to identify the magnitude at least one frequency. We've done that here with the minus 46. We need to identify the corner frequencies. One is at 1 radian per second, the other corner is at 200 radians per second. And then we need to identify the slopes of each segment. So this segment is flat, it's 0 dBs. This segment goes down at minus 20 dBs per decade, and this segment then goes down at minus 40 dBs per decade. So it's not the best picture, but hopefully you get the idea. We then go ahead and do the same thing for the phase plot. So looking at the phase of component A, it's just a simple gain and it's positive. So its phase is a constant 0 degrees. This simple pole, it starts off at 0 degrees and ends up at minus 90. And the break starts, so the break frequency for this pole is 1 radian per second. And so we start to break down 1 decade early, and we finish 1 decade later. So we're at 0, we start to go down at 0.1, and we finish going down at 10. This is component A, this is component B. We do the same thing with this simple pole, where the break is at 200. And so 1 decade before that is 20, and 1 decade after 200 is 2000. So we start off at 0 degrees, at 20 we start to break down, and we finish at 200. That's component C. And then the next step is to sum the components. So looking at low frequencies, all three are at 0 degrees. So we sum them. we get 0 degrees. Our first break comes at 0.1, and it goes down, it continues to break down until 10. So between 0.1 and 10, we have two components that are flat and one component that's going down. Okay, and then at 10, we have 0 plus 0 plus minus 90. It goes down. And then between 10 and 20, they're both flat. All three are flat. So we're flat. And then at 20, one of them starts to go down again. So we have two that are flat, one that's going down, and it stops going down at 2000. And at that point, we have one component that has a magnitude of 0 and two components that have magnitudes of minus 90. So 0 plus minus 90 plus minus 90 is minus 180. Okay. And so this is our Bode diagram. We have identified the corners. We have a corner at 0.1, a corner at 10, a corner at 20, and a corner at 2000. We identify the relative slopes. So we're flat, we're down, we're flat, we're down, we're flat. And we identify the phases at low frequencies and high frequencies. So as omega goes to 0, our phase is 0 degrees, and as omega goes to infinity, our phase goes to minus 180. So that's what our phase plot looks like. Taking a look at this, let's think about what this tells us. So we have a transfer function with a pole at minus 1 and a pole at minus 200. And so based on what we know about which dynamics will dominate, this pole is much faster, the pole at minus 200. So its effect will be negligible. And it would be well approximated by something like this, with just the pole at minus 1. And if we were to graph the step responses, they would look almost identical. You'd have two step responses. They'd look very first order. You'd hardly be able to tell the difference because the one pole is 200 times faster than the other, which is quite significant. This was sort of the situation that we've seen when we looked at DC motors, where the electrical dynamics are much faster than the mechanical dynamics. So if we were to do a step response for a system like this, you would have a hard time identifying the higher order pole, the faster pole. With a Bode diagram, however, you can see both the effect of both poles. So here you can see the effect of the first pole, but you can also see the effect of the second pole. And this is one of the advantages of the Bode diagram, is that you can see the effect of higher order poles. They're not hidden. You can similarly see the effect of zeros. If we were to have a 0, you could see exactly how it affects the magnitude and exactly how it affects the phase. Okay. To finish out filling out our library of components, we now need to address complex conjugate poles and zeros. So those poles and zeros that are underdamped. And so looking at this just really quickly, we in essence have something with no zeros and two poles. And so the behavior of this system is going to be somewhat similar to this previous example, where we had a second order system, where the magnitude starts off flat, and then at high frequency it goes to minus 40 dBs, where we get minus 20 dBs for each pole. And same thing for the phase. At low frequencies we'll be at 0 degrees, and then at high frequencies we'll be at minus 180 degrees, where we get minus 90 degrees of phase lag for each of the two poles.